Hi, in this video, I'm going to talk about how we can transform tensors, right? In general relativity, we have different objects. We have vectors. We now know we also have these objects called tensors, which might have a higher rank. And in special relativity, excuse me, we want to see what these objects look like in different reference frames. And so that is to say, if we want to consider we have some vector, which maybe represents the displacement of some object, I can observe that in my reference frame here in my office, or you're driving by in a car. What does that displacement look like to you as you drive by in a car? And so this displacement vector is going to look different to you than it does to me. And so we need to transform our vector to see how it will look in that case, it would be a boosted reference frame. So we've seen that our four vectors, we transform them by acting on them with a Lorentz matrix. Now we have this new technology of using these indices and of tensors, and this Lorentz matrix actually is a tensor itself. And if we, for instance, let's start with transforming four vectors as a very tangible example. If we have some four vector A new, if we want to see what it looks like in some new transformed reference frame, we're going to use lambda, capital lambda, as our transformation tensor. And notice that these news here are contracted. Right, there's my iPad's not wanting to work, but I think that's okay. And we're left with some A prime mu, where A prime is the four vector in the new reference frame. And our Lorentz transformation matrix, A mu nu, for, again, let's use the same example for a boost in X. It's the same matrix that we've been using all along, which is gamma minus gamma beta minus gamma beta gamma. All right, so it's really sort of the same thing that we were doing before. We're just writing our Lorentz matrix with our index notation. Now, what if we want to say we start with a excuse me, a four vector in the primed frame, and we now want to transform it to the unprimed frame. So let's think about transforming from prime to unprimed. So basically, I want to do the same equation that I just wrote here, except I'm assuming now I'm given A prime and I want to find A. Well, we just use the inverse transformation metric here, or matrix, excuse me. So lambda inverse, we find the inverse of that matrix, which again still is going to have these two indices, and this is going to give us an inverse transformation. Whereby inverse, of course, if I do a transformation and then an inverse transformation, it should look like doing nothing. So what I mean by this inverse is hopefully something familiar. If I do a transformation and then an inverse transformation, or I could consider doing it in the opposite order. These should be equivalent to doing nothing. And by nothing, that should be our identity or our Kronecker delta. Which note, this Kronecker delta looks sort of like a tensor. It's not, it's a symbol. Notice I am breaking my own rule. I wrote the indices right on top of each other here because it doesn't matter in this case. The Kronecker delta symbol is something that takes on its identity matrix. No matter what reference frame you're in, it always takes on this value. This is always. It's not something that changes, and there's no rightness or leftness of our indices. So it's just the Kronecker delta symbol. And it's identity, so it's doing nothing. So when I say I'm going to apply an inverse transformation, then this is what it should look like. Now, for some of these, it's easy to find. So for a boost in X, so if we do a boost in X where, the reference frame is moving to the right, the inverse is just going to be moving to the left. So to find our inverse transformation for our boost in X, literally we just send the speed, which beta here is really where the speed is carried, or the velocity, to inverse beta. So this is going to look like, this is going to correspond to gamma plus gamma beta plus gamma beta gamma. All right, and you can check for yourself that if you multiply those together, then you get the identity. So indeed, this is going to be an inverse. And then you can do similar things for different transformations. Of course, we keep using this one example of our transformation matrix, but you can look at different ones for different transformations. All right, so that is how we can use this index notation to transform our vectors. I guess before I finish this video, all I told you was how to transform 4 vectors. What if we want to transform a higher rank tensor? You're going to need a transformation matrix for each index. So for a higher rank tensor, you need a Lorentz transformation matrix for each index. So you should think about each of these matrices is going to transform one of our indices. And this will become clearer as we start to see examples and things like that. But I'll just leave it at that for now so that you know how to deal with higher rank objects. Thanks.